Here we are, ladies, and I guess ladies, I'll call you all ladies. Radical review. Okay, what we're looking at is chapter 3. Okay, chapter 3 deals with radicals. We looked at them briefly in chapter 1 when we talked about graphing, but now we're looking at them in a little bit more detail. You've dealt with radicals in grade 10 and 11. I'm just going to give you a quick review, rundown / reminder of all the things you are expected to know at this point. Okay, so first of all, what the hell is a radical? Well, this symbol right here is the radical, right? The radical, the index is this number up here, so it could be a square root, cube root, fourth root, fifth root, and the radicand is what goes on the inside. Okay, just a basic, the basic premise of what radicals are. Now, we have two different types of indices, right? The plural for index is indices. So an even index would be something like the square root of x, right? Now, if you have the square root of x, first of all, you don't need that 2 there, right? It's the same thing as saying just the square root, the radical of x. You could put the 2 there if you want, but you don't need it. As soon as you start getting into cube roots, however, and fourth roots, you need to know the index, so we have to put them in there. Now, with the even indices, or the even index, okay, we know that the value in here has to be greater than 0. So in this case, x has to be greater than or equal to 0, right? Because you can't take the square root of a negative number. Now, or the fourth root, or the sixth root, or the seventh root, right? So in this case, x has to be greater than or equal to 0 too. And if I have the fifth root of x, and then the sixth root of x, well, it's the sixth root again where x has to be greater than or equal to 0. Okay, now with the cube roots, if you remember what the graph looks like of a cubic equation, well, there's a lot of connections here, okay? If you look at the parabola, that's a y equals x squared, right? This is actually the inverse, so it comes down here. Now, that's not a function anymore. Remember we talked about all this? Now, if you have a cubic relation, there it is like that. And if you do the whatever it's called, the inverse, you get something like that, which again is the inverse, but that is a function. So when we have a cubic or a fifth root or a third root, then negatives are allowed because, for example, -2 cubed is -8, right? So with this we have the domain would be x is all real numbers. There are no restrictions. And again here, x would be all real numbers. Okay, so what we're talking about here, this is the domain, these things, okay? The domain and range, what x values are possible. So we are going to be looking at domain and range. I just wanted to remind you quickly about even and odd indices, okay? You can take the cube root of a negative number. Remember, the cube root of -8 would be -2, and the cube root of +8 would be +2. But you can't take the square root of, well, you can take the square root of 4, but you can't take the square root of -4, okay? Now, when we actually take the square root of 4, well, this is the next thing I want to talk about. I want to talk about something called the principal root, okay? If I asked you what the square root of 4 is, you're going to tell me that it's 2, and that's absolutely right. It is only 2. That's what we call the principal root, okay? You do not put plus and minus 2 in here. Okay, if I ask you what the square root of a number is, you give me the principal root, which is the positive root. Okay, now the only time you do a plus or minus is when you're solving an equation. Okay, so when solving an equation, we include the plus minus. So for example, if I said x squared is equal to 9, okay, and I asked you to solve this, well, the process is taking the square root. And when you're solving an equation and taking the square root, this is when you put the plus or minus in front. So it means that x is equal to plus or minus 3. Okay, so there's a difference between the principal root and the square root, okay, solving an equation using square root. So hopefully that clears up that little issue. Now there are a couple things that you should be knowing how to do, and one of them is simplifying radicals. So let's look at these and see if you can simplify them. And what we have to understand is that we have what we call perfect squares, right? Now since this is a square root, if we can identify a perfect square in here, hopefully you can see that it's 25 times 2, right? And if we break this up, it becomes, we're allowed to break them up because it's multiplication. Again, addition would be different, but multiplication, we can actually split them up. The square root of 25 now becomes 5, and the square root of 2 is just stays like that. So this is an entire radical, and this is what they call a mixed radical. We can do the same thing with cube roots, okay? Now you have to find a perfect cube, however. I'm not quite sure how familiar you are with your cubes, but what we can do here is 27 times 2. And then we have the cube root of 27 times the cube root of 2, which gives me 3 times the cube root of 2. So 3 times the cube root of 2. Okay, you got to start being careful here because this index here up front, sometimes it gets confused with the number up there, so we can mess that up pretty easy. Now, I got a list of perfect squares and perfect cubes here for you, just so that when you are simplifying these radicals, you know, having a list like this in front of you simplifies the process pretty easily, makes it quicker, okay? So you can take a couple minutes, I'll leave it there for a sec, pause the video. If you want to copy them down, okay? This is 343, so whatever number is here is right there. So if 2 cubed is 8, it means the cube root of 8 is 2, right? It's just an untying thing. You can see now that we're talking kind of like inverses, right? You do it this way, and then boom, you undo it and get back to the original number. 3 cubed is 27, cube root of 27 is 3. So inverse of functions, opposing functions, all right? We're going to be looking at graphs very quickly, but let's just sort out a couple other things here. So radicals and exponents. Now, hopefully you understand that they are intrinsically related. They are essentially kind of the same thing, okay? If we look at this here, right, if we have the index y, a to the power of x, we can rewrite this as a to the power of x over y. What this means is that if I have the square root of 9, there's probably a 1 here, because there's always, and there's a 2 here, so this is equal to the power of 9, or 9 to the power of 1/2, okay? If I have the cube root of 15, that's going to be 15 to the power of 1/3. Now sometimes you might have an exponent on the inside, so say you had, for example, the cube root of x squared, right? First of all, what type of restrictions would you have in here, or would you have any? Well, anything that gets squared becomes positive. Cube root, you can cube root anything. So we need to think about those steps before we start identifying domains and ranges. So if I wanted to convert this to an exponent, x to the power of 2/3. This is some process. This is a process that helps you in solving equations, and it's going to help you down the road too if you decide to pursue calculus and deal with harder algebra, okay? Another thing I wanted to touch on here quickly was negative exponents, okay? A negative exponent means it becomes a positive when you put it somewhere else on the bottom, or if it was on the bottom, for example, if I had x to the negative 3 here on the bottom, that would be x to the positive 3 on top. So negative exponents, please don't forget that. Also remember that anything to the power of 0 is equal to 1. So there's a lot of things to remember, okay? And we're going to be going through them one by one here. So now, manipulating radicals. When we group them together, for example, like combining radicals, okay? If I have a root 5 and a 3 root 5, hopefully you remember that since they are similar radicals, you can just say, okay, well that's 4 root 5. If you have root 2 plus root 3, you can't combine those at all. It has to stay that way. Okay, this cannot be simplified at all. But when they have the same radical or same radicand, you can combine them just like if they were variables, okay? Now, what about in a situation like this? These look completely different. Well, hopefully you can see that there are perfect squares in there so that we can simplify them, right? Root 20 becomes the square root of 4 times 5, which is 2 root 5. Root 45 becomes the square root of 9 times 5, which is 3 root 5. So what you're going to have is 2 root 5 minus 3 root 5, which is negative root 5. Okay? And the like. We're going to have lots of those. You could have cubic ones, okay? Obviously, you wouldn't be able to combine a cube root and a square root. That's like saying you can combine an x squared and an x cubed. The only way we'd be able to do that is if we actually multiply. Now, when we multiply, okay, this is what we talk about here. Mixed radicals to whole radicals. So, if I was going to give you something like x times root 2. And you want to make that an entire radical. You want to put that x back inside there. You're going to have to square it in this case because it's a square root. So it becomes x squared times 2, which is the square root of 2x squared. Okay? We'll have a similar one here. If I have 3 root x, well, if I want to put that in there, I'm going to have to square the 3, which means I put it back in and I go 9 times x, and that's just the square root of 9x. Okay, and if you understand it, this is kind of the same as simplifying them, right? If I want to take the 9 out, I have to square root it. It becomes 3 root x. So we're going back and forth here, okay? Let's look at another one here. If I had x square root of x, what do you think that would end up being if I wanted to make it a whole radical? Put the x back in. X squared times x gives me the square root of x cubed. And if you wanted to put it in exponential form, it'd be 3/2. Okay? Hope this is ringing some bells, folks. The last couple here we're going to look at 2 and then the cube root of x. Notice that I put this in brackets, not to confuse it, because sometimes if you write this, what's the problem, right? Does the cube here belong to the 2, or is it a cube root belonging to the x? Always a good idea to put brackets just to make a little more sense out of it, to make it a little more clear. And now if I want to put the 2 back in here, I don't square it, I have to cube it. 2 cubed is 8, so it ends up being 2 cubed times x, which is, and the cube root, so the cube root of 8x. Okay, let's look at the last one here. 1/2 x, I want to put that back in there. So I have to go 1/2 x cubed times x, and it's going to be the cube root there, right? Which is going to be equal to the cube root of, well, 1/2 cubed is 1/8 x cubed times x is x to the power of 4. There you go. You can rewrite this a couple different ways. So it's going to be the cube root of x to the power of 4 over 8, right? Interestingly enough here, let's look at this thing. If I have the cube root of x to the power of 4 over 8, okay, don't forget that you can also do this, the cube root of x to the power of 4 over the cube root of 8, which is x to the power of 4/3 over 2. That's another way to look at it, okay? This manipulation of radicals, folks, if you have a grasp of that, it's going to make this chapter much easier. Don't forget to have a look at 3.1. Hope this helped.